There are four types of cardiac muscles. The atrial and ventricular muscles are contractile and functions just like any other muscles. The special excitatory are still muscles but functions more like nervous tissue. We have the sino-atrial or SA node, also known as the Keith-Flack fibers, which is considered the pacemaker of the heart, being capable of spontaneously generating action potentials or impulses. We also have the conductive fibers, which includes the atrioventricular or AV node, also known as the Aschoff-Tawara, and the His-Purkinje network. Another distinct characteristic of myocardium or the cardiomyocytes is having a plateau in the action potential curve. However, as you may see later in our discussion, not all cardiac muscle types have this. The SA node, the atrial muscles, and the AV node have a P curves similar to those of the skeletal muscles. How are APs of cardiomyocytes initiated and conducted? It is mediated via the spontaneous electrical activity of the pacemaker cells in the SA node. Then, the AV node and His-Purkinje fibers conduct the APs throughout the other parts of the heart. What makes the sino-atrial or SA node the pacemaker of the heart? Cells of the SA node have an inherent leakiness to sodium ions. They also have an RMP of only -55 mV. These cells undergo a rhythmic discharge in which the RMP rises to nearly -40 mV, which activates sodium channels, leading to rapid entry of both calcium and sodium ions, causing an action potential. Repolarization occurs when the sodium channels become inactivated and potassium channels open. This illustration shows the action potential curves of the various muscles of the heart in relation to the ECG waves. But first, we need to mention again that the plateau in the action potential curves are not found in all cardiomyocytes. As shown, the SA node, atrial node, and AV node have curves similar to that of skeletal muscles. Myocardia showing plateau are those found in the ventricles, which includes the common bundle or the bundle of His, the bundle branches, the Purkinje fibers, and the ventricular muscles. Now let's discuss the step-by-step phases of the myocardial action potentials or impulses. Phase 0 is the initial rapid depolarization, as shown by this very steep, upward part of the curve. It corresponds to the opening of voltage-gated sodium channels or fast sodium channels. Phase 1 is the initial rapid repolarization, which corresponds to the closure of fast sodium channels and at the same time, the opening of voltage-gated, transient outward potassium channels. Phase 2 is the subsequent prolonged plateau. What happens here is that there is subsequent, but prolonged opening of voltage-gated calcium channels, or slow calcium channels, which allows flow of both calcium and sodium into the cardiomyocytes. At this point, there is decreased membrane permeability to potassium, which is about 5 times, thus decreasing the efflux of these ions. Basically, the plateau in the AP curve of ventricular muscles is due to the very slow repolarization as a result of the prolonged retention of positive ions inside the cells. Phase 3, which is the final repolarization, to Phase 4, which is basically the return to the resting membrane potential, are both due to the closure of calcium-sodium channels and opening of various potassium channels, allowing efflux of these ions. Now let's discuss refractoriness, or the period of non-responsiveness of cardiomyocytes to impulses. Like skeletal muscles, cardiac muscles have certain periods during their contraction-relaxation cycle wherein they are unresponsive to stimulation at threshold levels. The absolute refractory period is during phases 0 to 2 in about half of Phase 3. The relative refractory period is from the subsequent half of Phase 3 to Phase 4. The cardiac muscle cannot be tendinized because of refractoriness.